We are live now.
Okay.
So, Karnit, you can begin with the introductions.
Sure. Yeah. Hi, everyone. My name is Karnindu Patnaik. Today, our session is navigating transactions, acid complexity in modern databases. So this session explores the evaluation of transactions and the implementation challenges and insight into distributed database environment. Today's session is going to be presented by Shiv Jha. Shiv is a staff engineer and lead engineer at Nutanix. He is a seasoned professional with deep expertise in database streams and application architecture. His passion for open source software and community engagement underscores his extensive knowledge and experience. So I'll request Shiv to start the presentation. Shiv, over
Sure.
to you.
Thanks, Kanindu. Yeah. Hi, everyone. It's a pleasure to be here and meet folks at SNEA. And I hope we will have a good session with whatever questions you have. Please drop them by. I love to answer questions, even if I have to skip some slides. I have, in fact, sort of marked some slides that I could I could skip without sort of messing with the flow of the session. So please ask questions, and I'll get to them mostly towards the end of the session. So let's begin. We will look at transactions. So most of the people I think who would be here would have heard of transactional databases and stuff, and it's probably not new, right? It's the old boring thing. But over last couple of years, I have been sort of reading a lot into for some personal projects how are transactions implemented, and that's where my curiosity on transactions, single node database, clustered modern database, how has it evolved over the years, what are the trade-offs and everything, fascinated me. And then I built this talk to talk to people around about the transactions in the modern world. So this is a bit about me very quickly. My areas of interest mostly have been for last 11 years I've been working. I first worked at MySQL, so the love for databases began there, and it's been there ever since. Streaming technologies, call it messaging or whatever, application architecture, love open source and communities, regular speaker, and I also organize some meetups and stuff in Bangalore. So love to have you there, and then let me know how this how this talk goes for you. If there are any questions, you can reach out to me on LinkedIn. There's a Telegram channel, a very small Telegram channel. If you're really interested into these kinds of things and you want to discuss those, then this is the link that you want to join. I'll leave these at the end as well in the Q&A section. So let's keep moving to the heart of the matter. We will first go through transactions. I'll not bore you too much with exactly what is atomicity, consistency, and stuff like that, because I would assume most people probably have read it somewhere back in their college or at work. So I'll only look at some very subtle things that as an application engineer, when I was a little bit more into writing applications day in day out, I probably didn't think too much. I thought transactions will just take care of all the bad situations and it will prevent me. So I would just take up my ORM and then save something, update something, right? And I would be like, yeah, fine, it works. But then there are a lot of other cases that now I think you have to be aware of, and that's what I will cover in this section. Then how are transactions implemented internally? I'll take a few cases, few failures, and see how we can get to a better design. And then from single node we will move to distributed, so we see how transactions have to happen in the distributed fashion, and then we will take some examples to see how these look in the real world out there. So what amazed me is that the first SQL database was there in 1975, like it's called System R, and for over 45 years this thing has lived on, and it still sort of is used in a huge amount of enterprises, right? Any web app you see, the largest ones, everybody uses some flavor of MySQL or Postgres or Oracle or SQL Server, maybe DB2. So any of these, right? And what also strikes me is that while it has been there for such a long time, the notion of what is an SQL database and what is a transaction has remained quite similar to what the original idea was, right? And over time, there have been other inventions where people said, we should not make databases like this. It complicates things. It's probably not scalable and whatnot. And then one example of that could be the last decade or so, where NoSQL was emerging, and I kind of sort of uh, now feel like there is a trade-off. But at that time, I was employed by MySQL. I was in the SQL camp, I think. But the NoSQL camp was born out of this movement that you have to forego transactions if you really want something that is highly available, that scales horizontally and stuff like that. So transactions have to go away. That's where you had a lot of these document databases, key value databases, and whatnot, right? And the SQL camp was just dismissive of them, saying, what, if you are really building something serious, you should be using SQL databases, right? Or transactional databases. To me, these are not interchangeable, but pretty much used like that. I'll get to that. But like I said earlier, to me, both of these were exaggerated as I see it now, retrospectively. And then there are trade-offs, right? And I'll not go too much into trade-offs today. That's not the idea of the session. But I'll quickly move to making you think why you should be thinking of different things when you implement some application using transaction semantics of the database underneath, and how much should you trust, right? ACID, I think most people would know, and it's been there since 1983. Again, something that has lived really, really long. A for atomicity, C for consistency, I for isolation, D for durability. Pretty much stuff that most people would probably know. So I'll get into some of my viewpoints, right, around transactions, and specifically atomicity, consistency, isolation, and durability, right? So although we sort of come up learning that these are SQL databases, these are transactions, and this is what it means and stuff like that, unfortunately, one database's implementation of ACID does not equal another database's implementation. These are quite different in a lot of ways, right? For instance, the one thing that has always surprised me is how isolation is defined in such a complicated way, right? I can bet most of you would have again read about this: read uncommitted, read committed, maybe serializable and whatnot, right? So there are four different things, at least in Postgres. And then there are different kinds of anomalies that these can sort of prevent you from, and you are supposed to choose and all of that. But in my years of writing applications, I have frankly not used a lot of those to choose for my use cases. It's complicated, right? And the devil is actually in the details, right? So it's not very clean, and it's different for different databases. While ANSI SQL has some definitions, the implementations differ for different databases, right? So for instance, your Postgres and MySQL are also quite different, by the way, right? When a system claims ACID today, it's not clear exactly what guarantees it provides, although those look very similar, right? And if you don't understand those, you could make subtle bugs in your applications. And ACID, to me, I think, has unfortunately become marketing term. Everybody wants to say that we support ACID, but do they stay true to what it exactly means with NC SQL? Does that even update so much, so frequently to accommodate all these databases? Are the questions that you should ask yourself, right? And then over time, on the last decade, when there was a lot of different NoSQL databases, there was this term called base, right? And then it even confused people more, saying, what is this? And is this also truly transaction, or is it not? And I'll leave that opinion to you. But what I want to point out here is that transactions are not straightforward, even though it looks like that when we read it. So I'll very quickly touch upon what these different things in ACID are, and then we will, along the line, keep looking at some of the things that you should think deeply when you think of designing your application around a transactional database. So atomicity, most people would remember, again, all or nothing, right? So basically what that means is you have a bunch of statements within begin or commit, and it may not exactly look like this begin and commit, right? I'll show you an example, for instance, going forward. So let's say the first 3 statements are executed, and then the database, for whatever reason, cannot execute the other 2. And we are here talking about a single node, just to keep the matters sort of simple. Going ahead, we will apply these concepts to distributed databases or distributed arrangement of the same databases. But if you have executed 3 and you can't execute the next 2, then you got to abort. And basically what that is supposed to mean is, for the application, it is supposed to make it easier for it to retry transaction, because pretty much nothing happened, right? But are retries really safe? I don't think so, right? It's not enough to say that I retry and it's all okay, right? Because what if the database executed the transaction, and while that commit was coming over to you, to application, the network was sort of dropping that commit, right? Then you may end up as in an application retrying the transaction, unless your transaction is written in a way that it is idempotent, or the deduplication is implemented. This could mean that it could have some effect that you were not intending to make. What if the error is due to the database server being overloaded? Again, I mean, you don't want to go retry in that case. Errors generally are of 2 kinds: transient errors, permanent errors. Permanent errors, even if you keep retrying, they will not be solved, right? Even if it is having some side effect. For instance, if you execute a transaction, and in the side there was an email being sent when the transaction was being done, right? So you can revert that now. That is not reversible. So that could be there, right? And it's remarkable how many places I have seen this in a lot of different applications across organizations where I have worked, right? And then the other case could be, what if your database said that I cannot execute, and as a client app, you want to retry the transaction, but the client died, right? So now that data is lost. Coming back to consistency, the C of ACID, all it says that certain statements about data have to be always true. This is one example that I'm reminded of back from the book I studied in my back in my college, and I think a lot of people would relate to this. So I'll very quickly skim through it. So 2 accounts, account A and account B in a bank, money gets transferred from one to another. At the end of it, after the transaction and before the transaction, the total amount should be same. So 300 and 300, and then we are consistent. But like you would understand from this description itself, it's not a property that the database itself can manage, right? It needs the application to work with it to manage this consistency, right? And probably this is the most weakly defined property in ACID that you should keep attention to. Isolation again, right? So if you look at this picture at the bottom, what it basically tries to say is that you are doing 2 transactions, probably from 2 different clients, and they will execute at the same time. Still, the effect on your data will be same as if T1 had executed first, committed, and then T2 had executed. And while that definition seems very, very simple, it's not exactly what isolation means. For instance, when you read up this text, it almost indicates like this is serializability, right? But if you look at the implementation details, it's actually, even for Postgres, it's implemented using snapshot isolation, which is a much weaker guarantee, right? So you have to be careful exactly what your isolation means. And durability, right? The database text almost always says durability means once you have written it and the database has committed, you can never lose data. In reality, you can always lose data, right? If it was a single node, very easy use case. The sort of data center was on fire, right? You can always lose data. But then you have to see what kind of distribution you want to do. Do you want to spread your databases across geographies and whatnot? And then you have to be careful about consistency, latency, and whatnot, right? So, but then there is only so much return if you try to touch the extreme. So know your use cases and know what durability exactly means for your use case, and where losing the durability is probably fine for you or fine to recover from. So yeah, I mean, the point through all those slides I was trying to make that it's not as simple as it our texts make it out to be when we read them first, right? I'll now quickly go just a little bit into implementing transactions, right? What are transactions basically, right? It's basically a fight that goes forever, right? You want to improve efficiency of the database, or you want to preserve correctness, and it's like somewhere in between that you have to make do, saying, you know what, maybe this much, this is what correctness is, maybe I can extend that just a little bit more to get more efficiency, and how much you move that lever on which side. Based on these, there are a lot of different database or database configurations that you have to look at. And to provide all of this framework, databases will generally end up giving you isolation levels. Again, 4 or 5 different things that I'll show you, and you will get concurrency control. So yeah, sorry. So coming back to this is a snapshot from Postgres documentation. Isolation levels are 4, and then there are all these anomalies. And I mean, like it very clearly says, although there are 4 levels, Postgres internally actually only has 3 implementations, right? And that is because of the way they implement multi-version concurrency control architecture. And then it clearly now says that, you know, what you read first is not what is exactly true if you go internally, right? So there are a lot of such cases. Now coming back to a single node transaction, right? How is it implemented? If you try to uncover the layers in a database, typically you will have a transport layer, database server talking to its client, or if it is a cluster database, within the database nodes, how do you communicate? Then you have query processor, including parsing and optimizing. And I'll skip these and I'll quickly move to storage engine. Execution engine is whether you want to execute it locally or remotely or both. So but then storage engine is where I wanted to focus more. In storage engine, you will typically have transaction manager. Transaction manager is what will try to give you all the transaction semantics. Lock manager will try to give you concurrency. Access methods are basically, if you look at Postgres, something called table access methods. If you look at MySQL, it's handler interface. Basically, these are interfaces beyond which storage engine makers can make their own implementations of how your data is exactly stored on the disk, right? And it would typically have a buffer manager. This is where your dirty page caches and everything is managed. And you have a recovery manager. You could have a write ahead log or something, or a redo log, to manage replication as well as redo slash undo kind of things. But if your database basically fails, then when it restarts, the recovery manager module will kick in and make sure it gets to a very good state that you expected, and only that then it says I'm live for you to fire queries, right? So this is all about a single node. This picture, by the way, is taken from this book called Database Internals. I have put the reference to it at the last slide, so you can. I would really recommend this book. A few chapters that I'll mark in the reference again. Now, what if you distribute transactions across multiple nodes, right? We saw how we would do it in a single node, right? And a lot of people, when I have this discussion with them, say that why not just broadcast this to all the nodes in the distributed cluster, and each of them do the exactly what thing we did, right? Maybe in a for loop, you say everyone do the exactly same thing that we were doing as a single node, right? Um, and I'll show you the problem. So the problem is, what does commit exactly mean, right? You have to see that. So in this picture, we said we have 3 database servers, and all 3 of you execute what you did for single node, everything that we learned earlier, right? Now, what commit basically means is that once you have committed, you cannot go back on that promise, right? That's the promise of committing. So in this situation, you have 2 success and the failure here. And because you cannot go back on commits, then these 2 dbs will be like they have committed that, and that effect is shown in the db. Maybe some other clients have already seen that data, and this is just failing, right? Because this can't revert, there is a inconsistency forever unless you go fix it manually, probably, right? um, But maybe there's another way saying, what about a compensating transaction? Maybe in these two DBs that could execute transaction, you could put a reverse transaction. It's added +1 in, you could put another transaction saying -1. But then do you want that to be on the database server, or do you want it to be on the app? And there are implementations of both kinds, right? On the app side, there is something called Saga pattern, right? So that you can use. But for the DB, it could be difficult as well. But there are DBs that try to take that on themselves, right? Or maybe you would have guessed by now that, what if we make a more simplistic model saying, only if all of them agree to commit, and they have committed, saying that, if I once say that I will commit, then they have to commit. There's no going back from there, right? That would probably work, right? And that's the premise on which atomic commitment works. Now, atomic commitment is like very widely adopted. So, I mean, this is something that you should probably hear out patiently. So what it basically says is probably quite intuitive. Having looked at the previous slide, a transaction will not commit even if one of the participating nodes votes against it, right? We have participants and everyone votes if they can execute the transaction on themselves, that specific node, right? Failed processes have to reach the same conclusion as the rest of the cohort. And this does not work in case of Byzantine failure. Byzantine failure basically means that everyone is just independent. There's no influencing and all those business. And if you make a decision once, you can't revert those decisions and things like that, right? So fairly okay with our database nodes in MySQL or Postgres or Cockroach, Yogabyte, Spanner, whatever, right? So we can get there. That's not a huge problem for us. But going ahead, these atomic commitment procedure is typically made by somebody called transaction manager or a coordinator node. Could be something else. This is mostly what they call it in different kinds of databases. And atomic commitment, like I said, is very widely adopted. So MySQL, Postgres, Amazon's DynamoDB, Google's Spanner, even in Kafka, producer consumers, you will see some examples of atomic commitment. If you've not heard atomic commitment, maybe you would have heard of two-phase commit, right? This is one way to implement atomic commitment. There are other ways to do it as well, right? But we look at two-phase commit because this is really well adopted. All the databases that I put as example in the previous slide, MySQL, Postgres, DynamoDB, all of them implement two-phase commit. So let's say we have three databases, and let's say the coordinator is the database 0 and database 1 and 2 are also writing this transaction. So the coordinator in database 0, that process orchestrates the whole process of getting consensus and executing transaction. So when the application, when the database server says that, I am fine, I am going to write, I am ready to make a commit, then you tell other people saying, guys, just go and try to see if you can write this data. And phase 1, tell me if you are ready to commit to saying that, yeah, I can execute this transaction. That's what prepare phase in phase 1 means. So in this case, the positive example, and we will look at the negative example going ahead, but in the positive example, both the database 1 and database 2 say, yes, I can execute the transaction. At this point of time, they cannot go back on this, right? At this point of time, the coordinator database 0 is collecting these acts in yes. And when all the acts are collected, nobody should have said no, right? Then you go ahead and say, okay, now go and commit. And then once coordinator from here says, okay, you have to go and commit, you have to commit as a database 1, right? You cannot go back from there. If you can't, you have to keep retrying forever, right? I know there are problems. We will discuss those, right? And then at this point of time, when the coordinator collects all the acts and decides to go and ask database 1 and database 2 to commit, then it will first write that decision in its log file, which is durable and fsync there, right? And then it says that you guys have to go and commit now. In between, if there is a failure, then we still stick to that decision. We will look at that going ahead, right? So this is pretty much what I explained earlier. So library within the database, or could be a separate process in the coordinator. When database is ready to commit, coordinator starts phase 1. Coordinator sends prepare request to each node. Are you able to commit? Coordinator tracks response from everyone. If everyone says yes, commit. Otherwise, even if one says no, abort, right? And coordinator must write down decision in its log on the disk to handle crashes, so that when it is recovering after writing this decision at any point of time, it knows where exactly it is. So what if our node dies, right? Maybe coordinator dies, or maybe one of the servers die. That's what we were touching upon briefly, and I'll explain that in the text in the next slide. But I'll probably either explain here, and the next slide we can skip. It's just the same things in text. So if the coordinator, after writing this decision to commit, dies, it is going to come back, recover to ask these guys to commit again with a transaction ID maybe, and if it did not write the decision to commit and died, it will not go ahead with the transaction. And because only after writing it asks for commit, it's okay. If that was written and communicated to the database 1 and database 2, and any of them die after that, then after coming back, they have to execute this transaction, right? Only then they can be live. So 2 points of no return. If a participant says yes and coordinator decides to come back and say, please go ahead and execute the transaction, the participant in database 1 and 2 in our previous slides, they cannot go back on that promise when they said yes. They have to execute, right? Whatever come way. If the coordinator decide once, that decision it cannot change ever now, because that it has written to its log and fsync to its disk. So if the participant said yes, didn't hear back from coordinator, it has to wait forever. Coordinator must persist decision before it sends participants. I told you that if no commit record persisted in coordinator, abort on recovery. So you saw that there are a lot of failure cases in two-phase commit, and it's a blocking protocol. So like databases can get to a state where they are waiting forever. So to handle these cases, there is something called three-phase commit protocol. Unfortunately, three-phase protocol is kind of difficult to understand. And there are ways to make two-phase commit less failure prone, right? So people, I think, prefer that over implementing a three-phase commit. Like I said earlier, two-phase commit is quite well adopted. Three-phase commit is very, very rare. It's there for you to see someone implementing three-phase protocol. Three-phase commit, sorry. Right, and by now you would have guessed that if you take a single node and implement a transaction there, or you take a bunch of nodes and distributed transaction will be slower, because to take that decision of commit, you have to make network round trips to all the participating nodes in the cluster, as well as the coordinator has to f-sync the decision and all of that. So in a benchmark that was done some years ago, it was reported that MySQL with the distributed transaction configuration is pretty much 10 times slower, which you would guess, right? Network calls and disk access are probably the slowest things in the world today. So what other choices do you have, right, apart from atomic commitment? So one simple thing that actually has quite good adoption is single leader. So for instance, Postgres or a MySQL could work with a single leader that you could select manually, right? Maybe it fails once in a while, once in 4-6 months, and you are fine to come appoint the leader again. Maybe you just put that in the config file, so it is the only guy which is the leader all the time, and you have some process that keeps track of it, and it goes down, it restarts and makes the leader again or whatever, right? Or maybe you are fine with automatic selection of leaders, right? And maybe even if it goes down, failover and everything is automated. But then you have to think that whatever you are trying to do with every transaction commit, you have now pushed the same problem to the database server starting, and then trying to get the same consensus at the time of servers coming up, right? At a different time, you have pushed the same problem. Although this happens very less frequently, but then you have to still solve for it, right? Some of the other ways in which other distributed data systems solve this is probably using something like a Zookeeper, which internally uses Zookeeper Atomic Broadcast Protocol. Zookeeper is actually quite popular. Pretty much every distributed system that starts out there and requires consensus starts with Zookeeper. It is getting some criticism these days because beyond 5 GB or so, if you want to keep so much data in it, it sort of struggles. So people have sort of, when they scale their systems a lot over the years, like a Kafka moved from Zookeeper to Kraft. There is a system called Apache Pulsar. They are trying to move from Zookeeper to some other stuff. etcd is a popular replacement as well, and this implements Raft. Raft actually has found quite a lot of adoption, a lot of different implementations of it, different languages and everything. You'll get the implementation ready-made. And Paxos is also quite popular. A lot of systems in that come out of Google use Paxos, like Spanner uses Paxos as well. But it's popular as something that is quite difficult to understand. So unless you have certain specific requirements, people prefer Raft over it. Or Zookeeper is a surprisingly well adopted system that people use. Or just think of it like, if you could not select a leader, you could probably have um, a group of people trying to have a global order of transactions, and everyone just follows that. That is one way. If you have time, probably read the Calvin white paper, or try to read the Spanner white paper. These are the systems that also influenced cockroach db, yoga byte db, and things like that. All these new SQL or distributed SQL databases are based on these ideas. Or maybe the other way to do it is saying, you know what, if my database servers are going down and that is causing problem, maybe I have to do something to make sure that the individual database servers don't get lost, right? Network you can't eliminate. That's what cap teaches you. But maybe these servers going down, at least that part of it can be solved. And Google Spanner solves it by saying, individual people participating in two-phase commit can be a group of nodes with a leader, and only the leaders will participate. I'll show you that in a diagram going ahead. If it is looking too complicated, don't worry. So I'll quickly take a look at some databases that put these things into practice. Aurora is something that is quite popular. A lot of people that are in AWS, which is probably a lot of new age SaaS companies, they try to use Aurora, which works pretty well. I have a very quick note on what it is internally. How is it different from the RDS offering? So it's a fully managed RDS thing. It's broke up the MySQLs and Postgres of the world to make a service-oriented design. So compute and storage have been separated properly, and the storage tier, like the one you see at the bottom, this part is quite nicely made. So you have separation of compute and storage, like you see here, multi-tenant scale-out storage. So you can keep adding. You see dot 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 here, right? So you can keep adding storage nodes, and SSDs come with it for data. The redo logs are segmented and spread across storage nodes, and they claim that they can give you 5x the throughput of regular MySQL based RDS, or 3 times the throughput of regular Postgres based RDS. Very quickly, trying to touch base on what Aurora tries to do is, on the compute side, the parts are similar. On the storage side is where they have reinvented what these originally Postgres and MySQL kind of databases used to do. The storage tier is where they have changed a lot of things, like redo logging, metallization of data blocks, garbage collection, backup restore, everything that you would think of in the storage layer. So let's see how Aurora implements distributed transaction, right? So Aurora basically is built on the premise that storage and compute are okay in the world of cloud today, and that is where Aurora is available. So network is the problem. So they really want to optimize for network chatter, and they are of the opinion that two-phase commit actually has a lot of network chatter. We want to sort of have a reliable way to do it with less network chatter and stuff like that. So Aurora uses quorum style distributed coordination. V is your number of copies of the data that you want to write. Let's probably take the example and then we'll generalize it. The example is there in the red ink. So let's say you want to, so they, in a typical setting, they would have 6 copies of data distributed across 3 availability zones in AWS. So V equal to 6. And then you write at least 4 copies. So 4 of them have to say acknowledged, I have written this, or I'm ready to write this. And when you read, you have to have at least 3. What that means is, when you have written something and you are trying to read, if you are trying to get at least 3 versions, 3 reads from different servers, because we wrote to 4, at least one of these 3 will have the latest data. right? So we can use that. We are not using something old. And if you are trying to write, you should write to at least half of it. So then you figured out that you took 4 nodes to write. So you, in your previous write, you would have written to at least one of these 4 nodes, right? At this point of time, you could reconcile the other nodes in an implementation, or you could leave it for eventual consistency to do that. But at least you know exactly what you want to write, you, because you are guaranteed to get the latest version of write from the previous transaction, right? So read copies plus write copies, these votes should be greater than the number of writes. Like you say 4 plus 3 greater than 6, and the number of writes, 4 should be greater than half of 6, which is 3, right? So now DynamoDB is again a very beautifully built system. So like I said earlier, I come from the MySQL world in my first company, and the first time I actually read DynamoDB paper, it opened my eyes to how remarkably well some use cases can be solved so nicely by a NoSQL based system, and it ties so well to what Amazon as a business wants to do at Amazon.com, right? So DynamoDB is basically, I see that I have a question maybe. Okay, this is his answered. So always on key value store, single key operations. Generally they try to maintain consistency, but in the case of failure, they are saying, you know what, I'll let consistency go off, I'm fine with availability, because that small window of unavailability could cost me a lot of transactions on my Amazon.com, a lot of orders on Amazon.com, which is costly for me, right? So they forego consistency for availability, and they're saying that, you know, in the worst case, what could happen is, I will never. So if you look at the Amazon's cart, right? You keep adding stuff to your cart. What they promise in DynamoDB is that you will never lose an item because of branching and versioning and stuff. In certain corner cases, you can see a deleted item reappear, and they have done this math saying, you know what, this will happen in very, very, very rare cases, and the number of extra orders that we could do because we were available at that time far outweighs our business than, you know, sending that extra item. So I mean, this is some system that I absolutely loved when I read. I would highly encourage you to go through the DynamoDB white paper, and then I'll very quickly try to explain how they do their distributed coordination. So they use this consistent hashing. So a key k has to be written. It's a key value database. So you hash k, and you have all these a, b, c, d, e, f, g, all these nodes, and k seems to fall between a and b. On the right of it, b has to write, and when you are writing to 3 copies, they will maintain a preference list saying B, C, and D have to write that data. If D goes down, then they will write in B, C, and E. And once D comes up, E and D will gossip among themselves so that E will transfer the data back to D. Right. So it's called sloppy quorum because it's not exactly the nodes defined in a way where they have to reply, but they maintain a preference list, which is typically that number of neighbors, starting with the first one, which is called initiator. But it's a sloppy quorum because it's not only BCD all the time; it could also be BCE and reconciled later to come back to D. This is called hinted handoffs. So in an example, if n is the number of copies you wanted, w is the number of votes that you wanted for write to be called successful, and r is the number of copies you want to see before you uh, are successfully reading value, then typical deployment will have n equal to 3. So 3 copies, 2 copies I want to see before I read in a successful way, and 2 copies for write, which means that you write on 3 nodes. Even if 2 of them can write, you are okay. Even if you try to read from 3, even if 2 can reply back, it's okay, right? So it solves for that case where network is not stable in one of these lines out of 3, right? And then they beautifully do that thing where in the preference list they pick the next one if one of these is down. So in those extreme cases when some of these nodes down also, they are pretty available. if you want to deploy, so different services in Amazon actually deploy Dynamo with different configurations of N, R, and W. So if you want a very high performance read, you can say that I'll put R equal to 1, and I don't want to be wrong, but I have low volume of writes. So I can say W equal to N. I write to 3 places, and I want to have a buy-in from all 3 of them when I write. And that is why when I am reading, if I get a response from any one of them, I'm fine. I'm not looking for 2 responses in read, right? So that way my read throughput will be very high. If you want to, on the other hand, maximize for writes, then you will say, you know what, maximize for writes throughput at the cost of read correctness, maybe. Then you say, I am fine with writing at even in one of those copies, and I'll go ahead and say I am done. And while reading, I am fine to maximize for throughput, right? And sort of I'll either read from all 3 of them, so I am optimized for correctness. And read, if I am fine with little bit of stale data and all, I could make it 2 or something, right? So it depends on your use case how you want to tune NRW, but a typical one is 3, 2, and 2. So I told you earlier, right? So transaction does not have to always look like a begin in the top and then different things and then different insert and updates and whatnot and then a commit. For instance, this is how a DynamoDB API for transaction looks like. So let's say this is a snapshot from the DynamoDB white paper. I have this habit of writing down notes and highlighting and everything when I read these white papers. So let's say this example is somebody wants to purchase a book, right? So Amazon first wants to do a check saying, this customer really exists. I have a copy of this book that I'll make sure with the inventory, and then I will make an entry in the orders table saying, there's an order like this, right? So you do all those 3 things as preparing in these variables: check item, update item, and put item. You put all 3 of them in a transaction write items request, and then you invoke the client to say, write this request. So that's how transaction looks in DynamoDB. We were talking that if the in two-phase commit, so DynamoDB uses two-phase commit, and how they handle this case when the coordinator goes down, right? We said if coordinator goes down, before making a decision to mark a transaction committed, it has to write in its log. But if it goes down after that, the other database servers will keep waiting forever, right? So to get around that, what Dynamo does is, so basically this is their architecture where they have transaction coordinator and these write to different parts of the database in 3 different tables, like we saw in the earlier page: orders, inventory, and customers. But if the coordinator goes down, right, the ledger is still there. This is where the decision of the coordinator is being written when transaction coordination is being done. So if this transaction coordinator goes down, recover the other transaction, probably in an active passive mode they were there, the other transaction coordinator comes up, it executes its recovery management, which goes through ledger trying to see what were the last decisions. If those are communicated, if not, communicate back to the participant nodes in those transactions. If they were not written, then you just abort. But the transaction coordinator can then take over from this ledger, because this ledger is the source of truth. The transaction coordinator itself is sort of stateless. Spanner is another very well made database, and I'll show you how they got around this problem with two-phase commit by making sure that the participants in the database transaction coordination don't go down so easily, because if they go down, then again the sort of you are stuck there, right? So Spanner is a distributed SQL database made around 2012 13s. It's available from Google Cloud, and the sort of Google Cloud customers can also use Spanner. It's used to be an SQL kind of protocol, but very different from typical NC SQL or Postgres or MySQL kind of SQL. This SQL dialect is a bit different, but they have similar stuff like rows, columns, and the values are versioned with timestamps. So you have that full history. Replication configurations can be dynamically controlled at very fine grain by the apps that are using Spanner. For instance, which data centers to use, how far from users do we want to keep data, how many replicas do we want to keep, how far apart are these replicas. So these are some things that the client of Spanner DB can make choices on. Client will also make sure that it can automatically fail over between replicas, and data will be dynamically moving between data centers to make sure that the distribution of data at all the times is equitable. And Spanner, by the way, has also been an inspiration for Cockroach DB, Yugabyte DB, and all. If you follow those kinds of systems, Calvin is another one that you should probably take a look at. So if you very quickly want to look at how Spanner looks internally, this is again from that Spanner white paper. You have database groups of servers in different zones. In a zone, you have a zone master which assigns data to something called span servers. Span servers themselves serve data to clients, and location proxy in between is like when the client wants to get data, it will tell the client exactly where in the span servers it can go and find data. And like this, you have different number of zones and number of zones. Placement driver is making sure that there is data being moved across these, for making sure that the distribution of data is equitable and it's not like one fills up and the other is still half empty and everything. So I was telling you, right, that there's a coordinator in two-phase commit and there are participant database servers. So what Google Spanner does is that these participating nodes in the picture, we said database 1 and 2, and 0 was the coordinator, right? So database 1 and 2. So those are not individual databases. In the case of Spanner, all those are groups of database servers. So you have a leader and its replicas, another leader and its replicas, another leader and its replicas. So you have three groups. So three people participating in two-phase commit. If this leader goes down, then the replicas can take over. And for that coordination of which one with the leader, you have a Paxos running internally. If the data that you are trying to transact with, if the transaction is only involved with one zone, then you don't have to go doing two-phase commit. If you are across these groups, then you have to do a two-phase commit. So by making sure that the leaders are participating in two-phase commit, they are making sure that the replicas are around there, so this whole thing will not go down, and then at least that much they are able to avoid. So in the next picture, I'll show you details of what these components are. This is what I just described. Paxos is there to make sure that there's a state machine to support replication and leadership and all of that. Two-phase commit, regular lock table to make sure concurrency control that implements two-phase locking internally. A tablet is a bunch of key value pairs, a bag of key value pairs with timestamp versions and stuff like that. And storage is basically Google's own file system called Colossus. So that's where we actually end. Like I said earlier, I have a lot of my own thoughts there when I describe that, but a lot of it is derived from things that I mentioned here. This book, Designing Data Intensive Applications by Martin Klipman, is one of my sort of favorite books. I have read this multiple times, cover to cover. Chapter 7 and 9 is where you really, really want to read up if you like the content that I presented. It's where I have also derived a lot of my opinions or knowledge from. Database internals, I have used a picture from that book, and there is a lot of other theory that I have derived knowledge from. The Spanner example that I just put is also described quite well there. Chapter 5 and 13 of that book is sort of very, very similar to the content we saw today. And then there are a bunch of white papers and other blogs that I have understood Aurora, Dynamo, Spanner, and all these things from. So I have written the names of these white papers. You can just find them on the web. And lastly, one of the engineers in the DynamoDB team has written a very beautiful blog. That's where I got that picture of transaction coordinator failing and using the ledger. The other copy of the transaction coordinator comes up and all of that. So this blog is again something that you should go through. So yeah, I mean, that is all I have. If you have any questions, please write them to me.
Shivji, we have one question.
Mhm.
Vince is asking, how can I get the certificate? If you
I am not sure what certificate this is talking about. So, I mean, if it is talking about a certification saying, yeah, I can go and commit this transaction. So, in different cases, it could be a regular two-phase commit or something that I described with quorums. In Amazon Aurora, sloppy quorums in case of DynamoDB. In case of Spanner, I just described. So, there are different ways to get this certification saying, yeah, you can go and commit. But I'm not sure that's what certificate here is. But yeah. I mean, if I did not understand your question correctly, please type in your question and I'll take a crack at it. Or if you have any questions, just put it there in the Q&A bar. And these are my social media accounts. You can send me a text on LinkedIn if you have any questions or doubts there. You want more references. YouTube is where I have a lot of other talks similar to this, recorded from previous conferences, meetups, or whatever. This is the Telegram that I was talking of, and then the slides are present on my SlideShare account. Thank you.
Yep. Thank you, Steve. This was a wonderful session and a lot of insight for distributed database. So to all the participant, I would say that Shiv has given his profile here. If anybody has any further question, you can reach out to Shiv, and he would answer those questions, whatever you have. And thank you very much, everyone, for attending this. Thank you, Shiv, once again. We
Thank,
will conclude the session here.
thank you so much for having me. Yeah. Bye
Thank
bye.
you. Bye.